Okay, what we're looking at today is a Heathkit IG-102 RF generator. This particular generator is in immaculate shape. The paint job is in great shape. There isn't any rust on it. There's barely a nick or scratch to be found on it. It's in marvelous shape. And I have upgraded it with modern BNC connectors, and did away with the old microphone button connectors. So now you can use a new set of leads, which I will provide, a brand new set of BNC test leads, as you can see. And we're going to run this thing through some tests to prove to you that it's in good functioning shape and in reasonable calibration. The Heathkit is a general purpose bench unit, useful for working on radios, setting IF stages, that sort of thing. It produces a reasonable sinusoid from about 100 kilohertz up to about 110 megacycles. It does so in 6 bands. And right now, if you look on my oscilloscope, you'll see that we are outputting out of this generator at 100 kilocycles, as is attested to by my frequency counter, which is connected in parallel through this T-coupling to the generator, so we can observe both waveform and frequency. Right now we are on the dial at approximately 100 kilocycles, and we are reading 100 kilocycles and observing the waveform. We'll raise this, and as we do, you can see the waveform changing shape, increasing in frequency. I'm going to go ahead and take this thing up to about halfway. We'll say about 170 kilocycles. The waveform, I can use the attenuator to bring the waveform down. Amplitude does shift on this generator. It's going to do it on all of them as the frequency changes, because the circuit's a general it's a general circuit. It generates a large number of frequencies. It does some better than it does others. It's more efficient at certain frequencies, so therefore you're going to get amplitude changes. You set your amplitude using the attenuator, coarse attenuator dial, and then you have the fine-tuning attenuation here. So right now we are at 170 kilohertz on the frequency meter. We have a clean waveform, and we are running at approximately 170 on the dial, maybe 169, something like that. Very close. So it's not intended to be a digital type of a unit. Its dial is going to be approximate, but it's pretty close. As we take it up now to 320 kilocycles on the dial, we see that we are running 326 roughly on the frequency meter, so we're 6 kilocycles faster than the dial says. And here's our waveform. Then we're ready to go to our next frequency range. Let's go ahead and drop this back down. And we advance to 310 kilocycles on the second band here, and we observe waveform. And we see we are running 310 to 311 kilocycles, so maybe a kilocycle high than what we read on the dial. But now as I take the dial up halfway, roughly 55 on the dial, that would be 550 kilocycles. We're getting 563 on the frequency meter, and the waveform looks nice and clean. Go ahead and take her up to 110 on the dial. Waveform looks good. We can go ahead and increase our horizontal frequency so we can see it better. And we are reading 1.11 megacycles. And this would be at 1.1 megacycles here. So we're 0.01 megacycles off as compared to the dial. Very, very close. Again, for a crude unit, that's really not bad at all. Here we are on the 1 megacycle to 3.2 megacycle band. This would be 1 here. And here's our waveform. And we are reading 1.01. So we are 0.01 megacycles off as compared to the pointer on the dial. Very, very close. Okay, let's go ahead and take her up to roughly be about 1.7 megacycles. We see that our amplitude has increased. I can use the fine attenuator to bring it back onto scale, so it's more efficient at this particular frequency. And we see that we are running about 1.74 megacycles, and we are set for 1.7. So we are 0.04 megacycles high. Not a problem. Let's go ahead and take her up to the full end of that spectrum. We should be reading about 32 now, or 3.2 megacycles. Frequency on the frequency meter is 3.22, 3.23, and go ahead and turn up our waveform. Still looks good. All right, we are now on band D, and we should be reading about 3.1 megacycles. I can see that our amplitude has decreased, so we are less efficient at this particular frequency, so I kick up the attenuator. And what I see is that we are reading 3.13 megacycles. I am right on the 3.1 megacycle mark, so we are 0.03 megacycles off, very small. We're a little 0.03 higher than the dial shows. Let's go ahead and put ourselves at halfway. This would be approximately 5.5 megacycles on the dial. I see that we are very efficient here, so I can turn myself down with the fine attenuator. And we are running about 5.65, 5.64, so about 0.04 megacycles high. Not a problem. Let's go ahead and turn ourselves to full scale. All right, we should be reading approximately 1.0, maybe 10 megacycles, if I'm reading it right. And what I'm seeing is 11 megacycles, so we're about a megacycle high as compared. Oh, I'm sorry, that's 110. Didn't read that right. Should be reading 11 megacycles. Okay, our band, our sinusoidal signal looks reasonable. We are running 11.1 megacycles. Go ahead and turn ourselves down again. We'll start the next band. Right, we are on band E now. E puts us back on the first arc. And what I am seeing is I'm seeing some reflections in my cabling here. If I was to remove the frequency meter, we see that we clean up. So we're getting a little distortion here because I'm paralleling signals. I'm going to continue to parallel so that we can read the frequency off of the dial. We are right now supposed to be reading 10 megacycles. We are reading 10.11. We see that we have a reasonable sine wave. And we go ahead and take ourselves up to the mid band. This would be approximately 17 megacycles. We are running 17.44. We see that we are running very efficient. I can turn this down and bring ourselves back onto the screen. And then we take ourselves up to full. And this would be 32 megacycles, which would be the end of most shortwave bands. I am seeing something a little more akin to a triangle wave than a sine wave, but I'm going to disconnect the frequency meter. So yeah, it's the loading of the frequency meter that was distorting the wave. We have a reasonable sinusoidal wave here without it. So when I connect back up again, we see that the distortion is evident again. This is at 32 megacycles, and we are running 32.7. So we're off on the dial by about 0.7. And then finally, the last band, 32 megacycles. This is band F, which is the innermost arc here. That would put us approximately 32 megacycles. I see that we have a very weak waveform here, and distorted. The distortion's going to be the reflections from the cabling. But we are running 31.36, 31.4 megacycles, and I am set for 32. So we're running just a little bit low now. And if I go ahead and turn myself up to mid-band, mid-band would be, oh, let's say it's 60. This would be 60 megacycles. I see that my amplitude has shot up tremendously. We are a lot more efficient at this frequency. And we are at 60.45 on the frequency meter. So we are 0.45 megacycles higher than what we read on the dial. And then finally we go to the maximum, and this would be expecting 110 megacycles. I am right on the 110 on the dial. My waveform is larger than my screen. I can turn down my amplitude, and what I am seeing is that I'm running about 100 and 101. Let's go ahead and make sure we have enough amplitude here. You know, my frequency counter is only supposed to be good to 100 megacycles anyway, so I bet you that's probably it. Let's try moving it. Alright, we are getting a stable reading now. 108.99. 108 megacycles. We expected 110. So we're 2 megacycles shy of the 100. Well, not even. 108.9, so 109. We're 1 megacycle shy of reaching the 110 on the dial. It's good to know. So we did it. I mean, this thing has gone through and tracked very well on the on the vernier dial. The frequency read on the dial is accurate to the frequency we read on the frequency meters, and our waveform has been more than acceptable all the way through. That's our maximum waveform right there, 110 megacycle waveform. Alright, the intention at this point is to show you that the modulation, internal modulation capability of this unit works. Right now we have an unmodulated signal on the screen. We are in the unmodulated position. If we go to internal modulation, we observe that the sine wave is now modulated top and bottom by a 400 hertz signal. And as I change my frequency, the upper frequency changes, but the modulation envelope doesn't. Now, this is looking at the high frequency being modulated by the lower frequency, and if I reduce my range on my scope, then I can demonstrate the modulation envelope where the lower frequency is being modulated. Well, it's modulating the higher frequency. So here's the 400 hertz envelope, and then in between is roughly right now about 5.5 megacycle high frequency. So we see that the modulation is taking place. Now if I turn the switch to external modulation, it goes away and we just have the high frequency waveform. So the modulation is working fine on the unit. You have your choice of either modulated or unmodulated signal. Thanks. So there you have it, a very clean IG-102 with the new style bayonet BNC connectors, with a new style BNC coaxial cable with the gator clip ends so that you can connect to your circuit wherever you want. I'll also provide a Heathkit manual. And the manual contains foldouts of the schematic diagrams, and they're on 11 by 17, so they're easy to read. And then we have all of the accompanying text for calibration, circuit description, troubleshooting, so on. So you're all set. Good luck on your bidding. Thank you.